Okay, welcome back everyone. This is session 7 on day 2 of the 2022 PhysiCell Virtual Workshop and Hackathon. Welcome to session 7. Hopefully you were just returning from session 6 a moment ago, where we built our first example going the full model workflow, going from creating a model in the graphical model builder first, then declaring and implementing C++ functions to modulate cell behavior based upon their environment, and then assigning them to the functions. We also went through some modifications to how to more manually place initial cells in their environment and how to change the coloring functions that were built in. And now we're going to continue that example and add some more functionality, kind of going into how cells interact. So we're really happy to have you back. So our goals here for this afternoon, for this session, is to introduce further cell interactions, a little bit more advanced interactions like advanced chemotaxis, phagocytosis, give a little bit more detail on the mathematics of that, cell effector attack, fusion, and transformation. And then we're going to extend our tumor immune example to have a little bit more of a detailed M1, M2 polarization axis, that cells are going to release pro-inflammatory factors in high oxygen and anti-inflammatory factors in low oxygen. And we're going to introduce a new cell population, CD8 positive T cells. These are the effector T cells or cytotoxic T cells. And they will follow pro-inflammatory signals, attack tumor cells, and create damage. And then we need to modify our rules so that damaged tumor cells will die. And if we have time, we're going to do a fun example, farmer prey and zombie, and we'll talk about that one when we get there. So let's talk about the mathematics of some of these interactions in the code. First, as a reminder, so this should go back to Anika's great talk on random migration yesterday, that standard chemotaxis uses a biased random migration, the key parameters being the instantaneous cell speed, the bias direction, the preferred direction of migration, the bias parameter between 0 and 1 that says how much you listen to that bias direction. Then the overall motility direction is the direction you actually choose, which may be different than your bias direction. And your persistence time says how long you travel along D motility until you choose a new direction. And so when it's time to choose a new direction, you are going to take a linear combination of a random unit vector and your bias direction. So notice that if B is 1, then you're going deterministically along your bias direction. If B is 0, you've got a completely random, basically a Brownian motion at that point. And then this is contributed to the overall cell velocity. You take the instantaneous speed times a unit vector along this motile direction plus all the other force terms. So standard chemotaxis says that you go into the model builder and you choose which one of your chemical substrates you're going to listen to, and your direction of bias is a unit vector along the substrate gradient, either against it or towards it, so a positive gradient, or against it, it would be negative gradient. So in your model builder, you'd go over here to chemotaxis, make sure motility is enabled, go to chemotaxis, enable that, choose which substrate in the dropdown, and then choose either towards or against. Advanced chemotaxis is an extension of this that we just very recently introduced. That, and in fact, this gets to some of the questions that were asked in the sessions yesterday, that we can do a linear combination of gradients for motility direction. And so now our bias direction is not just parallel to one gradient, but a linear combination. And the way this works is any weight or sensitivity that is positive means you move towards that gradient. If the weight is negative, then you move away from the gradient. And of course, if the weight is 0, then you just ignore it. And so the way you would do that is, instead of enabling chemotaxis, you check the box for advanced chemotaxis, and then you choose a debris from your dropdown, and then say what its weight is or its sensitivity is. And so remember, those can be positive or negative. And then there's also an option to make it a linear combination of the normalized gradients. And so sometimes you might want to use that. So now we have a more advanced chemotaxis we can do. I want to point out some of the data structures that are available in the code for your use. First of all, there's this neighbors list. So if you go into cell.state.neighbors, this, I think we discussed a little bit the other day, but it is it's a vector of cell pointers. Any cell that was found by the mechanics function to be within an interaction distance is added automatically to that neighbor list. And that is going to refresh every mechanics step. And so automatically updated. And so that can be useful for other common interactions. And then phagocytosis is a built-in method, which you've already seen. You can have phagocytosis of dead cells or phagocytosis of specific types of live cells. And so you go over to the interaction tab, you pick your cell definition, and then for that cell definition, you go and you can either enter that dead phagocytosis rate or the live rate. So pick from the drop down, choose some type of cell you want to phagocytose, and then set a rate for it. And the implementation is that if a neighbor is dead and in our neighbor list, then with probability, our phagocytosis times delta T, we have the likelihood of phagocytosing that dead cell. Likewise, if one of our neighbors is live and it has type I, then we go and we look up our phagocytosis rate for live cells of that type times delta T gives us the probability, and that's we roll the dice, and that's our probability of phagocytosing them. Now, if we do phagocytose the cell, we absorb all of their volume. So the fluid volumes get combined. You basically imagine that you're kind of engulfed the cell, and all the solid contents get added to the cytoplasm of the eating cell. And we also absorb the internalized substrates of the target cell into the phagocytosing cell. And interestingly enough, this does not change the target volume of the cell. So now the cell's temporarily big, so it's going to start shrinking back down towards its original size, which is like a basic model of digesting the stuff that you just ate. And this is processed every delta T mechanics. And then we already talked about how to get it in the model builder. Another key interaction is effector attack. So you go and down to the next spot in the graphical model builder to attack rate, pick which kind of cell you're looking at attacking, and pick a non-zero rate. And so our attack is the rate of attacking a specific live cell of a certain type. We don't attack dead cells in this formulation. And then if we are attacking it, we're going to increase its damage at a rate of R damage. And so in the implementation says that if a neighbor cell is alive and in type I in our neighborhood list, we're going to look at that attack probability by calculating the probability of the attack rate times the delta T. That's how the probability of attacking that cell. And if we do decide to indeed attack it, then we're going to increase the damage to that victim cell, the cell that we're attacking, by R damage delta T. And so notice that we're going to basically be adding up the cumulative attack time on cells, because you could have more than one cell attacking cell that could gang up on it. I want to point out that right now, any one effector cell is only allowed to attack one cell at a delta T. So they might attack, jump and attack different cells by this model, but they're not going to be attacking like 5 cells at a time. They're going to direct their ire in one direction at a time, according to the built-in model right now. The other thing I want to point out is that this effector attack is increasing damage in the target cell. But for that to actually result in cell death means you need an additional hypothesis that says that cell damage increases your death rate. And so that's where you're going to need the C++ functions to fully implement this. Right now, it's not built in, although we're thinking about it. Fusion is another possibility. And I know there's some people who are attending who are interested in it. And so this is very similar to attack. You could say that, let's say macrophages, you choose a cell type and say, who do you want to fuse with? And for any cell that is possible to fuse with, you have a non-zero fusion rate. And so it's implemented very similar. If a neighbor is type I, then the probability of fusing with it in any delta T is the fusion rate times the delta T. And if that happens, you combine the volumes, combine the subvolumes, and the internalized substrates. And the other thing is we combine the nuclei. So if cell 1 has 1 nucleus and cell 2 has 2, now you have 3 nuclei total. We're going to put the new combined cell at the center of mass. Oh, and this is one more thing that's interesting. I don't think we actually said it. Target volume. So the newer, bigger cell keeps the larger size as its target volume, so they won't shrink after it. This is not phagocytosis. This is not eating. This is actually like a merger of the cells. Okay, so the target size for the merged cell will be bigger, and so this is in the interaction tab, just like everything else. Okay, and then the last thing is transformations. So this says that any one cell type can transform into any other cell type with a probability, again, of the specific transformation rate times the delta T. And this is something that could probably use some future refinement, maybe some more nuanced handling of some of the internal variables. Right now, basically, if you switch from type A to type B, you take the definition from cell type B and completely copy it. So you're going to lose some information during that transformation right now. So this might be an area for refinement. Okay, so we're going to take these built-in capabilities and we are going to improve this tumor macrophage model. So we're going to have the macrophages secrete pro-inflammatory factors except in low oxygen, and we're going to secrete anti-inflammatory factors in low oxygen conditions. So pro-inflammatory M1-like outside the tumor where there's higher oxygen, and then M2-like when they get into low oxygen regions. And then effector T cells are going to follow the pro-inflammatory factors by chemotaxis. They're going to attack the cancer cells to increase damage in those cells. And if they encounter anti-inflammatory signals, they're going to slow down the rate of attack and they're going to slow down their chemotaxis. And cancer cells, when they are damaged, will increase their rate of apoptotic death in our model. So our checklist here is we're going to plan. So we'll figure out the mathematics. Then we're going to iteratively add any new diffusing substrates. We're going to add the T cells, and then we're going to update our cell definitions as much as we can. And then we will find the phenotype functions in C++. Update the cancer rule to get the death, create a macrophage rule now to get this change in secretion, and we will make a phenotype function for the CD8 positive T cells to vary their behavior with the anti-inflammatory signal. So let's do it. So first we plan out the mathematics, and so I'm going to use a Hill response type function for the tumor cells, saying that you have a kind of a background death rate, this D0, and that as your damage increases, your death rate gets higher and higher and higher towards a maximum death rate. And so we're going to use this kind of thing. We're going to assume that the maximum death rate is 100 times greater than the background death rate. We're going to pick a half max of 180, Hill power 2. I'm just kind of pulling basic numbers to say that I'm going to try to pick a sharpish transition and say that when you reach 180 minutes of contact time with cells, that you're going to start getting a sharp increase in your death rate. And then macrophage rules, we're going to vary their secretion with the oxygenation. So I'm going to use I'm going to basically use a different Hill function varied with the oxygen. So let's see here. There we go. They're going to vary with the oxygen that the secretion of pro-inflammatory is greater in high oxygen values with a half max of 5. So here we're at the half response curve. That the anti-inflammatory is inhibited by oxygen or allowed by low oxygen. And so we can see this trade-off, this switch in behavior between pro-inflammatory and higher oxygen values and anti-inflammatory in lower oxygen values. Oops, I think I have my label backwards here, so I really apologize for that. I'll have to fix it. We'll pick a half max of 5 and a Hill power 4 just to have a fairly sharp transition. And I think all the teams with more experience in pharmacokinetics and pharmacodynamics will probably be able to have a lot of insight on how to calibrate these values in the future. And then we need the T cells. The T cell behavior needs to vary with the anti-inflammatory signals. So we're going to say that the cell speed slows down the more anti-inflammatory factor you have, and that the attack rate also slows down the more anti-inflammatory factor you have. So you kind of take the base rate from the cell line and then scale it with this Hill response function. So when the anti-inflammatory signal is low, you're at 100% of your normal value, and then as the anti-inflammatory signal increases, then you start going down towards no behavior. And so again, I've picked these kind of for convenience for a phenomenologic function. These are not calibrated parameter values right now, so I want to point that out. So we've done our planning. We have our microenvironment. From these different models we talked about, we have a handful of new parameters, Hill response functions for death, for changes in the macrophage behavior, changes in the CD8 positive T cell behavior, and of course we need this new cell definition. So checklist, we're done planning. Now let's start doing. So we're going to go back to the model builder if we're not already there. We're going to open that config file and save it, and we're going to go and start modifying the microenvironment. So here, we're going to just save this. I'm going to go to the microenvironment, and I'm going to click on debris, and I'm just going to copy this diffusing substrate. I'm going to double click and rename it to pro-inflammatory. And I'm going to set the diffusion coefficient at 1,000, just to kind of give it some pretty good movement. Decay rate of 1, but take the square root of 1,000, or 10 to the 4th divided by 10 to the 0. That's 10 to the 4. Square root that's 10 to the 2. So I have a 100 micron diffusion length scale. My initial condition should be 0 and no flux conditions, so no Dirichlet conditions here. And that's my pro-inflammatory factor. And I'm going to copy it again, double click, and name it to anti-inflammatory. And I'm going to give it the exact same transport characteristics. So we have these two new signaling factors in our environment. And let's go ahead and save it. And just double check that we truly see these changes in our configuration file. So go into config, open this. And now we see we have oxygen, we have debris. You know, they didn't show up. So this is a concern to me. That sometimes there's this kind of lack of synchronization between the model builder and what shows up in the saved file outside. I'm not sure why that is. I'm going to try save as and try to manually write over it. Yes, I truly do want to replace it. I would love to see my update here. But I'm only seeing debris. I'm not seeing my other substrates. Just kind of click run because sometimes that forces a write. Yep, there we go. As you see now, these new factors showed up here in the config file, so that's a relief. So I guess we'll just let that run and keep building. So let's see here. I have two comments. Yeah, I'm seeing that there can be weirdness between file buffers and that not everything shows up right away. It seems like clicking run will force it to kind of flush out. So hopefully that will continue to hold. Thanks, Joe. And you can see how hard Randy's had to work on these tools to deal with these weird oddities. And I'm so grateful for it. Let's go ahead now and continue through we added our diffusing substrates. Let's add the T cells. So I'm going to go back into the model builder. And let's see, it looks like it's just about done running. I do a couple things actually. I'm going to let this run. I'm going to change my, go to my microenvironment, now go to cell types. I'm going to click on my macrophage. I'm going to copy it and rename that to CD8 positive T cell. Let's make sure that we got the same spacing. Yeah, there should be a space here and a space here. I just want to keep it consistent. And let's see what we have here. I'm going to, save it. We go to cycle, and I'm using, I have no birth rate, no death rate, because we want to just leave a fixed immune cell population. Volume I'm going to leave alone for now. Mechanics, I'm going to leave that alone too. And go to motility. I'm going to leave all these motility parameters alone, with a bias of 0.5. The only difference is that we don't want macrophages to be following debris. We want macrophages to be following the pro-inflammatory factors. So we change to pro-inflammatory in the dropdown, make sure it's all enabled, and hit save. And then we're going to change some of these secretion characteristics of CD8 T cells. In particular, we want to make sure that they are not eating debris. So I'm going to set the debris uptake to 0. And then I'm going to take the pro-inflammatory. These should not be secreting anything. And but they should be uptaking pro-inflammatory because they're, in the process of binding to the ligand in the environment, that should be consuming a little bit of ligand from the environment. So I'm just going to pick a moderate value of uptake rate of pro-inflammatory factor and a moderate rate of uptake of the anti-inflammatory factor. So let's double check here. We are consuming oxygen, makes sense. We are not consuming debris. We are uptaking pro-inflammatory and anti-inflammatory. So that looks pretty good. And now let's go to the interactions. This is where it gets really cool. So we go to the interactions tab and we make sure we have the CD8 T cells selected. And these are not allowed to phagocytose dead cells. We set that rate back to 0. And now we want to make sure they attack cancer cells. So we go here to attack rate and make sure that we have selected cancer in the dropdown. And I'm going to pick an attack rate that's really high for now. And actually we'll find that we'll need to shut this down much lower, but I'm going to pick 10 for now. This says that they ought to be attacking somebody at every delta t 0.1 time step. So there we are, right? So we've turned off phagocytosis for T cells and turned on a damage rate, an attack rate for the cancer cells. So let's compare, right? Macrophages, dead phagocytosis, no attack rate. T cells, no dead phagocytosis, and it does have an attack rate on the cancer cells. Okay, and then let's go to custom data and start adding these variables in. So let's see, we're looking at changes in the T cell line. So let's keep T cell selected and go to custom data and add a new variable called CD8 half max, which I'm going to pick to be 0.5. And then a new variable called the Hill power for that response function. Remember, we picked a really steep response curve with a power of 8. Okay, so we've made our T cell definition. And now let's update our macrophages. So go back to macrophages now. So select that over here in the cell types. And we're going to go over to secretion. And I'm going to set my secretion rate. I want to make sure that, let's see, we have debris being consumed, but in particular, macrophages need to be secreting the pro-inflammatory factor. So I'm going to set a high secretion rate of pro-inflammatory factor towards a target of 1. So we actually do get secretion. And I'm going to set the anti-inflammatory secretion also to 10 and 1. Because now, if I don't write in C++ rules, this is bad. They're going to always be secreting both all the time. But what we're going to do, right, is we're going to write that C++ function that modulates both of these secretion rates based upon the signaling in the environment, based upon the oxygen that they're encountering. So hit save. Let's just double check here. We have oxygen uptake, debris uptake, pro-inflammatory secretion, and anti-inflammatory secretion. That looks pretty good. And let's go now into custom data to add these few variables that we need. I need a variable called M1, M2 half max. This is for the macrophage behavioral changes. We'll give that a Hill parameter of 5. And we'll add an M1, M2 Hill power. And we'll give that a fairly steep curve of, with a Hill power of 4. So notice I've added this custom variable to macrophages. So this one has non-zero parameters here, whereas the other ones don't. So we have that. So now we've updated macrophages. Now let's update our cancer cells. So I go to cancer cells. I'm supposed to add some custom data, which I forgot to type in my slide. I apologize. So I'm just going to look at my screen cap. So I'm going to select cancer cell here, go to custom data, and start adding what I need. I need damage, half max. And that value looks to me like it ought to be 180. And then I have another parameter called damage Hill power. And it looks like that needs to be 2. And then I need relative, no, sorry, actually damage relative max death. So this is how much death increases compared to the baseline with a high amount of damage, and that should be 100. So go ahead and just save that. And let's see where we are. And then we need parameters for CD8 T cell placement. So let's go over here to user parameters. These are like the global parameters, not cell type specific. And I'm going to make a new variable called number of CD8 T cells. That should be an integer parameter. And let's start with 50 T cells. And then I'm going to make another parameter called T cell distance, basically, saying how far out should those T cells be. Let's make them 375 microns out. Now, if you're writing this not in real time, have more time, you should fill out your units and a description of these parameters so they make sense to other people for better reproducibility. But for now, we're just going to go fast. Okay. Oops, I don't know where my, okay, so I accidentally went back. Sorry about that. We've added our custom data for cell placement. And if you need to catch up on the code, if you unzip session 7, checkpoint 1, this will catch you up with where we are right now in the code. Just going to hit save. I'm going to go over here and click run again, since that seemed to kind of flesh out the file rights and just make sure this is actually doing what it's supposed to be doing. So if I go here to settings now, I should see all these new custom parameters like number of T cells and the T cell distance. So that looks right. It looks like our file did indeed sync up with what we expect. And the code is running now. So in fact, we can kind of go back to the initial placement. So hit back. Oh, but we don't have any T cells, right? We haven't written the code yet to start initializing the T cells, nor have we updated our coloring function to color them differently. So we have a little work to do yet, but we are definitely getting there. Okay, I'm going to take a look at the chat window. And Furkan is posting a link to get the code for this session. Thank you, Furkan. Really appreciate that. Now it's time to declare custom functions for the phenotype of these two new cell types. Or I guess we didn't need one for macrophages, but now we do. And then we need a phenotype function for the T cells. So I'm going to go back into custom.h. Remember, header files where you declare a function. And so we'll go ahead and declare these two new functions. And then the CPP file is where you implement them. So we've declared them in the header. And now we're going to update the cancer phenotype. So I'm going to go into the phenotype function we already wrote. And all I need to do is I need to add another block of code that will vary the death rate based upon the damage. And so I'm going to first get the amount of damage that I have based on this, using this get single signal function. So get the damage. I'm going to figure out what the base rate of apoptosis is. That'll be like my B naught or my D naught in that mathematical rule. I'm going to go and get the parameters from my custom variable. So custom damage half max to get my half max, custom damage hill power to get my hill power. And then my rate max is going to be this relative value times the value, get single behavior. And then I use my hill response function. I'm going to just, I find it easy just to say, evaluate my hill response function based upon my signal, in this case being the damage, my half max and my hill power. This will be a number between 0 and 1. And then I will modulate my overall rate. It will be my base rate, some linear interpolation based upon this hill function. So this will give us our hill response. And once we're done computing the updated rate, we'll set the single behavior from my cell, set my apoptosis to the new value. So let's go ahead and paste that into our code. So go here to custom.cpp, and we are going to look for, here's our cancer phenotype. And I'm just going to add the stuff to the very bottom of the function. So hopefully this starts getting more and more familiar as you do it, right? That our basic mode of operating, right, is to say, I'm going to get a signal, which will be the input of our model, do some kind of manipulation of it based upon, say, getting reference values from my parent cell line and other things. And I'm going to calculate an updated rate for this behavioral parameter, and then write the behavioral parameter back to the cell using these dictionaries. So we've updated a cancer phenotype. Now we need to create the macrophage phenotype. So we already declared the function. We just need to implement it. So let me just kind of walk you through this following the same paradigm, right? Takes a pointer, takes a phenotype by reference, and how long to update your model. We're going to sample the oxygen at the cell's location. We're going to get parameters for our response function from the custom variables. And then we're going to calculate a hill response function that we're going to vary based upon oxygen between, oxygen, half max, hill power. And we're going to modulate our rates, saying, it's going to be the base behavior of secretion, of anti-inflammatory secretion, inhibited by oxygen, so 1 minus hill, and then set my behavior. And then the pro-inflammatory is the opposite way. You get the base behavior, and then say that the higher the oxygen value, the more we have the secretion. So I'm just going to copy paste all of this and put this at the bottom of my CPP file. And now I have a macrophage phenotype. Okay, we're working our way through our checklist. This is actually going okay. So now let's go ahead and create the T cell phenotype. So here, let me walk you through it. Same functional form, pointer, phenotype by reference, DT, mistyped motility. All right, and let's see here. I am going to query the environment to say, what is the current value of the anti-inflammatory signal at my position? So I'm going to get single for the anti-inflammatory. Then I'm going to get my parameters from my custom variables. And then I'm going to compute my hill response function, saying, based upon my anti-inflammatory and my half max, my hill power, where am I on that hill response curve? And then I'm going to get my parameter value is going to be my reference value times 1 minus hill. So remember, the more anti-inflammatory signal this gets, hill approaches 1, 1 minus hill approaches 0. So my migration speed is going to go down and down and down. So I get my reference migration speed, and then I'm going to get that kind of get a modulated value, and then write the modulated value back to the cell. So write to my cell single behavior of migration speed and take that parameter value. And then the same thing, we're going to use the exact same Hill response curve to inhibit cell killing. So I'm going to go and get a single base behavior, get my, so the format here is going to be attack and then a target cell type. So attack cancer is my behavioral value. So I'm going to get the base value from my cell line, modulate it by this Hill function to get this decreasing killing rate as the anti-inflammatory goes up, and then write that behavioral value back to my cell. And that's it. So we've already copy pasted that into our CPP file. So now we have created the phenotype functions, but we need to assign the functions to make sure they actually get used. So when you go into the create cell types and see, so go over to create cell types and oops. Here we go. So create cell types. Remember, this is where we assigned the functions for the cancer phenotype. And we're going to copy in that same syntax. Find the definition for macrophage and assign it to the update phenotype function. Find the definition for CD8 positive T cells and assign that function. And we're ready to go. Now, if we were to run this, we'd find it was disappointing because we haven't actually placed any T cells. So we should probably, I'm missing a few steps in my checklist here, really. We need to make sure we place the T cells. So we're going to go into setup tissue. We're going to add a little section where we place the T cells. Remember this functionality, right, is to find the cell definition for T cells. And then I'm going to go through and say, based on my parameter value that says how many I need to place, I'm going to place them on a randomly on the unit circle and scale that radius out by the distance, and then create a cell and assign its position. And so let's paste that in to set up tissue. Scroll down here. I'm just going to make another section of placing the T cells. And now we are able to place T cells, but we should probably also update the coloring so they look right. So I'm going to change the coloring from macrophages to go from a bright red when they're M1-like to being white when they're M2-like, based upon how much anti-inflammatory they're secreting. So we'll just do a linear scaling based on that. And then we'll color all the T cells green. And so we're going to go into the coloring function. First, I'm going to add a little section to color the T cells. So notice that, I'm going to compare my cell's type name to CD8 positive T cell and make sure that it's not dead. And if so, I'm going to make the coloring kind of a dark green, kind of like an olive drab. And so go find this coloring function. So remember, we need custom coloring function. Here we go. So here we start out with the number and paint by number coloring. We color dead cells differently. Now we're coloring live tumor cells based upon the proliferation rate. And we're going to color the T cells based all green. And then we're going to make sure that we update our coloring of our macrophages. So here we're going to say if I'm a macrophage and I'm not dead, I'm going to get my current secretion rate of anti-inflammatory, so anti-inflammatory secretion, and scale that by the maximum secretion of my parent cell line. So that'll be a number between 0 and 1. And then I'm going to scale it, right? So let's see here. This is basically going to say I'm going to start off as red, so always 255. If my secretion is 0, this would be 255.00, so for bright red. And then as my secretion rate goes up, these guys approach 255, so I end up at a bright white. So let's go ahead and put that into the coloring. So I'm going to color the macrophages based upon their secretion rate. Okay, let's see where we are now. Now we've changed a lot of code, so we better recompile it. So I'm going to go to a command window here and type make and recompile. It's always a relief when it actually does compile. And let's go back to the model builder and run again. So let's see if I can find that window. So I'm going to click on run simulation. Watch for that bar. Okay, so now it's actually running. And notice the output says it was placed in the T cell, so that's a really good sign. Let's click on legend. Now we see we have completely different coloring. That cancer is, between zero and between zero and yellow, macrophage between red and white, and my T cells are green. And go to the plot. Let's go to the very beginning, and let's plot against the pro-inflammatory factor. So at time 0, nothing's been secreted yet. Go 1 frame. You see how all these macrophages are secreting a lot of pro-inflammatory factors, so they're bright red. You look at anti-inflammatory, they're barely secreting at all, so there's not much there if you look at the scale bar. And so let's follow through, right? We see how the macrophages are going to be doing their random migration towards dead tumor cells. And they are secreting pro-inflammatory factor that is attracting the T cells to follow along with them. So now those macrophages are kind of burying themselves into the tumor, and the T cells are following along. T cells are coming into contact with tumor cells and attacking them, causing damage. And you see, some apoptotic cells being left behind from these T cell interactions. So we can kind of click play here and see how the pro-inflammatory factor is following along. But now notice the macrophages are reaching hypoxic tumor zones, and they're changing to more of a cancer-associated macrophage type. They've been phagocytosing a lot of dead material, and they're starting to secrete a lot of anti-inflammatory factor now, and that should now be kind of dialing down the behavior of the T cells. And we may actually need to dial it down even further to get a more realistic model. But we have all the basic pieces. We have tumor cells that are varying their birth and death with oxygenation. We have dead cells that are releasing debris. Macrophages are attracted to debris and phagocytosing dead cells, and they are secreting pro-inflammatory factor except when they're in low oxygen regions. Pro-inflammatory factor is attracting T cells, and they start attacking tumor cells upon contact. And then if there is a lot of anti-inflammatory factor, that slows down the behavior of the T cells. So we're getting to get a fairly sophisticated model that really only took us not too much time to build. So I'm pretty happy to be able to get there. So yay, it all worked. We compiled, we tested, we built everything. We have tumor cells, we have macrophages with a kind of a polarization axis, and we have T cells that are actually able to not only damage cells, but that damage is causing death in the tumor cells. And so we can just kind of play around with parameters at that point. But what I'd like to do, though, is instead move on to our bonus example, because we actually have about a half an hour left. So I think we are on pace. I think we're going to do this. So let me take a break for a second and say, are there any questions before we proceed to the next example?
So Paul, I have a question.
Mm-hmm.
For the initial configuration, I know what you did makes perfectly, like initial configuration makes perfect sense. I'm wondering, like, how effective is the initial configuration? Like, eventually, like, since we are talking about somewhat random process, like, is that going to converge to the true behavior after some point? For example, if I just initialize T cells, I don't know, like on the upper left corner, and then tumor cells somewhere else, when we run the code, eventually that's going to converge to what we wanted?
That's a really terrific question. The initial placement will make a difference. If you were to put all of the let's say macrophages in one corner and all the T cells in another corner, you might find that they're kind of all lodged in one part of the tumor and neglecting the other half. So that initial placement will make a big difference. Now, if you're placing them a little bit more randomly like we are, it should converge, I think, over time. But if they're starting off in one corner, it's going to take a long time for them to get over that basically that directional bias you've built into your initial conditions. So it can be really interesting that way. Another fun thing to do, actually, is instead of introducing a big bolus of tumor cells and macrophages and everything else at the beginning, what you can do is you could actually make another function where you may want to randomly nucleate and create new cells at random times and at random positions. And that might help come over some of those biases. But that's something you could put into the main loop of your code if you wanted to. And so that could be fun. Joe, did you have a question?
Yeah, I'm really glad that you guys added the state neighbors thing now. I was curious If I had an object, a cell object, and I had a really long interaction distance,
Hmm.
uh, I know previously you had checked for neighbors by checking the mechanics voxel Moore neighborhood
Hmm.
around that cell object. So if my interaction is like, uh, 10 mechanics voxels away or something,
Yeah.
will that neighbor get added, or is that too far away?
That's a really good question. I'd have to think about that. I think we would need to increase the size of the mechanics voxel for that to happen, because I think it only still picks basically that Moore neighborhood. Uh, and so for cells of typical size, it will be fine. But if we have wildly different sizes, we may need to keep doing it more manually like yours. But then we
Um,
can use the add to neighbors list, for example. So I think for yours, you may still be in this business unless we change the mechanics voxel size.
uh, and that was my kind of follow-up question then was, I noticed in the that paper you guys did with the liver mechanics that you had done, I think it was you had made a second mechanics mesh. So you had like two different sizes.
Hmm.
I'm asking because I was trying to see how you guys had done that because it seemed much faster than what I had done,
Yeah.
which was sort of the manually check brute force approach.
Yeah. I'd have to remind myself. I really apologize. I'd have to go back and
Yep,
look at
yep,
that code and see how we did it. But there are definitely some possibilities to do things like that. Um, in this case, too, you may even want to think about like custom mechanics functions that look nearly the same as their own the new ones, but have a more customized search, for example. Like you wouldn't want
yep.
small agents testing everywhere, right?
Right, right.
It's mostly the big agent that needs to test everywhere. So you may need like a custom mechanics function just for the big agent. Is one
Okay.
possibility. But we'd have to think about that. Make sure we do it in a thread safe way. That gets tricky.
Yes. Yeah, that's the
So let's touch base on that one later on. I think it's a really good point. Okay, these are great questions. Let's let's mute my stupid phone and move on to the next example here. I think you guys will get a kick out of this. And so what we're going to do is we're going to make an example basically designed to test out some of the other capabilities. So usually I would do farmers, prey, and predators, but now I'm going to make them zombies. And so the idea here is that farmers are going to be releasing food. These are prey, which are basically the townspeople, port people, or Selly people, small community. So the farmers are going to be releasing food, and they're going to be chemotaxing down gradients, so down the gradient of food. So they are basically trying to wander to wherever there's little food, they want to go and make more food. Prey, or townspeople, will be consuming food, and they will be reproducing at a rate proportional to their food. So more food means more reproduction, less food means less. And let's see here. And then they will be releasing a quorum factor. So it'll be kind of like some of the bacteria models you saw yesterday. The prey will be releasing a quorum factor, so it will help them to find other prey so they can aggregate. They want to also look for food and also stay away from zombies, which means that we're going to need the advanced chemotaxis function for this. And then if the zombies attack them and cause damage, then they, instead of dying, this will be a different pharmacodynamic model where here the increase in damage is going to increase the transformation rate from townspeople to zombie. Okay. And then zombies will be attacking prey, looking for prey by chemotaxis. So I probably should put this first in my bullet point. So I'll update these slides later. Attack prey. They will eat dead things. And then this will be fun. This is for you, Dee. Whenever two zombies come in contact, they have a probability of fusing to become a mega zombie. And that mega zombie will have a higher damage rate because it's bigger and tougher, but it will also be slower. And then, there will be a possibility that townspeople could fight back. And so if they cause damage to the zombies, then they can die, which will get interesting when the zombies start eating dead zombies. So full workflow, we're going to plan the model, populate the template project. edit in the model builder to build the domain, environment, cell definitions, custom variables, and then we'll define the phenotype functions just as before. So here's our checklist. I'm going to not worry about placement of cells or coloring or any custom parameters. So we're going to make this a pretty easy model as far as that goes. And so let's plan. So let's talk about the mathematics of our poor townspeople here. So they're going to proliferate at a rate proportional to the food availability. So this will be kind of a really basic model here. And the speed will be faster. So the better fed our townspeople are, the better they are at running away from zombies. So we're going to scale the speed linearly with the amount of food available to them. And then zombification, we're going to use a hill response function saying that the more damage you have, or more damage you've accumulated, your faster rate of transforming into a zombie. And so we'll use a hill response function with a half max and a hill power. Okay, and let's look at the zombie math. If zombies merge to become mega zombies, they're going to have more than one nuclei in our formulation. So we'll use nuclei as our way to figure out if they've become mega zombies. And so we're going to say that the speed should decrease the more merged you are with kind of a gradual half max power. And that, on the other hand, that the mega zombies are stronger, so we're going to scale their damage rate with the number of nuclei, and then death is imposed by damage. So just like with the T-cell model, we say that if townspeople attack the zombies, they have a probability of succumbing to their injuries and completely dying instead of being undead, I guess. So that's what we have. We have a variety of custom variables stemming from these custom response models. So we're planned. Now we need to basically get back to a clean starting point. I'm going to go ahead and close the model builder just to make sure we're fully clean out. I'm going to type make data cleanup to get rid of all of my simulation data. Make reset, get back to a blank slate. Make template to kind of go back to that template project. And then make to compile the template project. So we're kind of back to our original starting point. Okay. And then we're going to edit the domain. I'm going to leave the spatial domain as it is. We're going to set the maximum simulation time to 2 days with outputs very frequently because I really want to see how these things are moving around. So let's open up that model builder. Let's see, what is it? It's Python / PhysiCell model builder bin Python model builder.py. And I don't know. I think I'm just going to go without the studio this time because I had a little bit of troubles with the studio this morning. Darn it. Nah, let's just go for broke. Python. Okay. So I'm going to open up the model builder. And I'm going to go here and I'm going to open up my configuration file. And click on open. I'm going to go ahead and save it just to make sure we're really working on that file. And I am going to change my maximum time to 2880. I'm going to leave the domain alone, virtual walls on, and I'm going to save SVGs every 15 minutes and the full data every 15 minutes. Hit save, just kind of make sure we're there. Okay. Next, I'm going to edit the microenvironment. So I'm going to go here to the microenvironment tab. I'm going to double click this generic substrate and rename it to food. I'm going to leave the diffusion coefficient alone, but I'm going to take a much lower decay rate of 0.01, an initial condition of 1 everywhere, and I'm going to disable the Dirichlet condition, no boundary condition, just 0 flux. Okay, so that should be good. And then I'm going to copy the food. So hit this and copy, double click it and rename it to quorum factor. So this will be for the townspeople. I'm going to set a much lower diffusion coefficient of 1000 and a lower decay rate of 1, initial condition 0. Go ahead and save that. And then I'm going to copy the quorum factor and make this zombie factor. So this will be secreted by the zombies. And I'm going to keep the same parameters otherwise. So let's see here. We have defined our environment. So check. Now let's create our cell definitions. So I'm going to go into the model builder and start working on the farmers first. So go here to cell types, double click default and rename it to farmer. And I'm going to change the cycle representation to transition rates for live cells, I think is easier. And farmers, we're going to make no cycling. So I'm going to leave this at 0 here. I'm going to go over and turn off deaths, make sure the farmers don't die. So it's basically like some kind of automated feeder, I guess. So cycle and death are done. You go to mechanics, and again, in this example, I'm going to make these cells unadherent, non-adherent, so 0 cell-cell adhesion strength. And then I'm going to go to mechanics, and first of all, I'm going to turn motility on. Then we're going to turn chemotaxis on, and we want these things to go down the gradient of food. So they are looking for areas of low food so they can go spread good food everywhere. Issy asked a question, if we get problems calling both the environment variable and the cell type zombie. Fortunately, we have not run into problems with that, but that's a really, really good kind of question to ask. Should be fine. Then we're going to go to secretion. We want to make sure that the farmers are planting food. So they are secreting food at a rate of 100. So they're really pumping it out. Set the target to 1 and save the model again. And we should be in good shape. Actually, yeah, we're already done with our farmer definition, at least initially. So in fact, you know, let's go to user parameters and maybe do like, say, 50 of each cell type. Right now, there's only 1, of course. Go to run, make sure, and this trips me up a lot, make sure you name the executable to the correct name. So our name of our executable is project. So, and this is the correct settings file. So let's click on run simulation. So we'll just kind of check and see what's going on with these guys. And say go maybe 1 frame. So here, look in the legend, I've got farmers only. If I do a substrate plot of food, you can see that, you know, substrates are pretty high, right? They're all pretty close to 1 and highest around the farmers. And if you play out, they're kind of wandering towards regions of low distribution. And actually, they're doing a pretty good job of kind of uniformly distributing themselves out through the domain. It should look very similar to a hexagonal packing. So I think there was a question yesterday about how to get self-avoidance. And this is one way to do that, actually, is to have them go against what is effectively acting like a quorum factor right now. So now we want to create the prey. So we're going to start. Let's see, hopefully the run is now just about done here. I think I'm going to probably set this to, I'm going to go to config basics and just set this to 1,000 so the simulations are much shorter when I'm testing. And now I'm going to go to the cell types, and copy, select farmer and click copy, double click it, and I'm going to rename this prey just to be safe for this time. And I'm going to go here back to cycle, and I want the prey to have a cycling rate. I want them fairly fast. I'm going to hit 1 times 10 to the negative 3. So that should get actually some fairly swift proliferation. I'm going to go to death and make it 1/10 of that. So 1 times 10 to the negative 4th for death, for apoptotic death. And save. And I'm going to go to motility. And for now, I'm just going to do standard chemotaxis. So they want to go towards the food because they are looking for it. So I change that to there. And then I go to secretion. I want to make sure that prey are not making food. They should be consuming food. So set the secretion rate to 0. Set the uptake rate to 10 just to give it a nice 100 micron diffusion distance. And I'm going to go and select quorum factor. And I'm going to make sure that their target is 1 and that they are secreting quorum factor. Okay, and save that. So now I've set up my prey to have a birth and death rate, to be moving towards food, and to secrete their quorum factor, which we will use soon. And we're going to redo the motility a little bit later once we add the zombies, and we'll do all the interactions at once. So we're kind of halfway through making prey. So now let's go ahead and make the zombies. So I'm going to go over here back to the cell types, click on prey, click on copy, and double click and turn that into zombie. And this is where we start having some fun. I'm going to make the zombies have a 0 birth rate. So they're going to have to attack townspeople if they want to make more zombies. The background death rate also to 0. And then let's go to motility. We want the zombies to chase the townspeople, the prey. So we're going to have them do chemotaxis towards the quorum factor. Hit save. And then we go to secretion. Zombies had better not be secreting quorum factor. That would be weird. Instead, they should be secreting zombie factor. So let's have them secrete zombie factor at a rate of 10 towards a target value of 1. Go ahead and save this thing. And then let's go to interactions. So zombies are allowed to eat the dead. So we'll set the phagocytosis rate at 0.01. And they are allowed to attack not farmers, but prey. So make sure you select prey in the attack rate. And I'm going to set an attack rate really high right now of 1. And we'll mess with this a little bit later. Hit save. And remember, zombies can fuse to become mega zombies. So this is for people who love cell fusion. I'm going to pick and say that zombies can fuse with zombies at a fairly low rate of 0.001, which we'll see it will not be so rare as you might expect. So hit save. And so now I have my zombie interactions, at least in the beginning form. So I've defined my zombies. Now starting adding the custom variables we're going to need for our phenotype functions. So I need to go, let's see here. Oh, I'm sorry, we needed a few more things. Let's add, let's now turn on the custom chemotaxis. So I'm going to click on the prey for the advanced chemotaxis. So go back to motility. I'm going to uncheck chemotaxis. And I'm going to check advanced chemotaxis. And let's see here and make sure it's enabled. And food, we want them to look for food. So I'm going to set my sensitivity of 10 to go up the gradients of food with a relative weight of 10. And then I'm going to pick a quorum factor. Say, they want to look for others too, but frankly, they're more interested in finding food. So my weight for that will be 1. And then zombies. We want to really prioritize avoiding zombies. So I'm going to set I need a negative weight, first of all, to go away from that gradient. And I'm going to pick a big value of -100. So that's the largest component to my linear combination of gradients. So let's see here. We have 10 for food, 1 for quorum, -100 for zombie. Okay, so that's a good place to be. And let's finalize the interactions. Let's go to interactions here. And let's have prey. So select prey here. They can do a very, very low rate of counterattack. So make sure they don't attack prey. Whoops, right? Let's have them attack zombies. Let's go ahead and set the rate 1, but they do a lot less damage, 0.05. Makes sense. The zombie's a little tougher here. And so, yeah, so we have that. And then I'm going to pick on zombie transformation. This is going to be basically the maximum rate of transformation is the way we're going to do this. So I'm going to set the rate of 0.01, and then we'll have to write a function to modulate it. So prey can turn into a zombie at a rate of 0.01. Go ahead and hit click save on that. So we've created all this stuff. Now start adding our custom variables. So I'm going to go over to prey and click on custom data. And I'm going to get rid of sample data and have prey transformation half max. So it'll be a hill response function with a half max value, I think of 5, it looks like. And then I'm going to have a hill power for my hill response function of 2. Okay, I'm going to save that. So I've added custom variables for my prey. Now let's add custom variables for my zombie. So I'm going to have the zombie speed half max. And it looks like that needs to be 2. Zombie speed hill power, looks like that's also 2. So I didn't paste that into the slides completely. And then the zombie damage half max, looks to me like that should be 20. And then the zombie damage hill power needs to be fairly steep. We put it at 4. So let's save that. I'm going to double check here in my my source file. Oh, it looks like the source file closed. Oh, okay then. Well, I'm just going to go right here and go into my custom data, custom modules, sorry, and just open these up in my default editor. Oh, and I'm going to open up my config file too and just see what that looks like. So let's make sure that the zombies got these custom data. See, it didn't quite right. And we do have this kind of flushing problem. So we click save. It does seem like if I click run, it flushes things out. And I click run simulation, and yeah, see the jump on the left, everything finally wrote. So we're gonna let that go. And if in doubt, I can unzip this checkpoint code if you need to get at it. So it looks like we did flush it out. I want to double check one other thing here. Go into the cell definitions. I know I've had a little bit of trouble with the advanced chemotaxis. There's some bugs, I think, in the toggles. So yeah, this looks good though. The chemotaxis is turned off. Advanced chemotaxis is turned on. That's looking pretty good. So let's look and see, let's see what we've done. Let's click on plot. Notice on legend, I have now 3 cell types. You can go back to the very beginning. You know, there's the food. Here's the quorum factor being secreted by the prey, and the zombie factor being secreted by the zombies. Now let's just kind of watch and see what these guys do. So we had a really high transformation rate. So all of the townspeople have been converted into zombies, and now some of them are merging into mega zombies. So hilarity ensues, and we've got 2 populations surviving here. So, okay, so we need to add our custom functions to get the rest of the behavior modulated. So we need to declare and implement the custom functions. So let's go ahead and first declare our functions. So we're going to go into the header file and declare phenotype functions for the prey and for the zombies. I think you'll be pleasantly surprised at how little we need to do to finish this model. So we declare these 2 functions, and now let's start implementing the functions. We'll start with the prey. So I'm going to copy and paste. Well, let me show you what we got. So prey phenotype, we're going to modulate the birth rate and the speed and the zombification. So the birth rate, we're going to get the base behavior of the cycle entry from my cell definition. I'm going to say how much food do I have, and then I'm going to do a linear response model to basically scale my maximum birth rate and then write that back to my cycle entry rate. Then I'm going to scale my speed, also with a linear response model, just to keep it easy with the, so I'm going to get my base migration speed and say that if I have more food, I am going to have faster migration speed. If I have less food, if I'm starving to death, I'm just not very good at dodging zombies anymore. And so I'm going to vary that speed. And then zombification. I'm going to go and the behavior I want to modulate is transform to, and then cell type, in this case, zombie. And I'm going to vary it based upon my damage, so get single signal damage. I'm going to get my half max, my hill power from my custom data. I'm going to calculate my hill response function. So saying that the more damage I have, the greater my transformation rate. And so basically, if I have no damage, my transformation rate, my hill response would be 0, which means I get a 0 transformation rate going all the way up to that 0.01 we had in the code. And I'm going to write that behavior back to the prey to have my response function. So let's go into custom.cpp and paste that in. So like a dozen line of codes, and we've got that fairly complex phenotype model for the prey. Let's see here. What next? We've got the prey model. We better work on the zombies. So zombie, we're going to do similar, right? We're going to set the migration speed, the attack, and the death. So first, migration speed. We are going to query, we need to find out if we are mega zombies or not, right? And so right now, there's not a custom, the dictionary does not have an entry for number of nuclei. So we need to go get that more manually for now. So we're going to modulate migration speed. We're going to go from cell.state.number of nuclei. That's going to be our signal. We're going to get my behavior parameters for my hill response function and then calculate it. That my modulated parameter value is my migration speed times 1 minus my whole response function. So it's like the more mega zombie I am, the more times I've merged, I get slower and slower and slower. It's just hard to walk around when you're a humongous zombie. And then I'll set my migration speed. Attack rate going to be similar. I don't want to modulate the attack rate. I actually want to modulate the damage rate just this time. That's not yet built into the dictionaries. It probably will be in 110.5 just because I realized now it's missing. So I'm going to manually go cell phenotype interactions damage rate, and I'm going to modulate that, scale it linearly with the number of nuclei. So the more mega zombie I am, the more I can cause damage. The faster it causes damage, and then write that parameter back to the cell. And then likewise, I'm going to do the death rate very similarly to the T cells. I'm going to query that damage. I'm going to get my heal response function parameters, and I'm going to modulate from no death all the way up to 0.01 for fairly fast death based upon the amount of damage sustained by the zombies. So I'm going to copy all that and define that function. So now we have defined the functional relationships between the signals in our environment, like damage, number of nuclei, things like that, to the key behavioral parameters in our model. So we've created these functions, but we have to make sure that we assign them. So that's actually not going to be too bad. We're going to go back up here to the create cell types code. You're going to scroll down, look for the comment that says, this is a good place to set custom functions. Okay, we'll believe you. So I'm going to hit paste here. So first find my prey definition, and then update my phenotype function with my prey phenotype. And then I'm going to find my zombie definition and override its phenotype function with the zombie phenotype function, the one that we just made. And I think we're ready to compile. So let's hit make. Remember, we changed our code, so we have to recompile. Oh, we got something funky. Get base behavior. Oh, we got a problem here. Sorry about that. Let's go back to the code for the zombie. Single base behavior, single base behavior. Where is it complaining? It's complaining at line 227. Here we go. Yep, get, it should be, I should have used get single base behavior. And probably one more right over here. You may notice by the, you may guess by the syntax that we can actually grab a whole vector of base behaviors or other behaviors if you want to. So that's a little bit more advanced of a usage. Here we go. Now it's going to compile. And let's go back up to the GUI and click on Run Simulation and see what it does. And when this is done, we should probably increase our simulation time so we can get a little bit something more interesting. Now we can go back here to the beginning. And let's see here. So we can see remember the prey are red, the zombies are yellow. You should be seeing that the prey are running away from the zombies, but towards the food. The zombies are in pursuit. It's actually pretty fun to watch. So we can see that the prey are forming aggregates when they can. And then the food source says, hell, that's where it's most depleted. So the food kind of catches up. And the zombies are going to be chasing those and turning them into more zombies. So I think our run is done. Let's increase the maximum simulation time. Let's do like 4,000, let's say. So we'll do run simulation. That should force a flush out to the file. So now it's running again. So here we can see the legend. We have these different cell types. Go back to the beginning. Let's look at the quorum factor just for the fun of it. So you see the quorum factor surrounding all of these prey. Now as we run along, you can see how the zombies are pursuing the prey. The prey are running away. It's kind of fun actually to see where two waves of zombies come from both sides and they kind of flush out the prey. They kind of run away. If they run from separate directions, they can even split little herds of prey. So that herd split over there. Oh, they got a few of these guys over here. They're attacking. I would expect if we go a few more frames, yep, you see we got a conversion. This guy turned into a zombie. Now, the interesting thing is it's a stochastic event, so you can actually have a delay before something gets zombified, but they don't know they're a zombie, so they're still running with the other prey, and they're still accepting that. So you can have you can have your neighbor turn into a zombie without you knowing it. Oh, and here are some mega zombies. Let's see what they do. See how they're moving slower now. So they're running slower, but if they manage to corner someone, they're going to do a lot of damage. So we have a zombie townsperson battle. So I think we've made it. We've got our full zombie model. So I think I might release this on Halloween at some point. So I think we're right at where we want to be. So I'm going to go ahead and kind of wrap up here. So we did a better test and things coming up now. So over the course of the last 2 days, we've introduced the basic workflow, the intermediate workflow where you model the environment and the basic cell definitions in the GUI. And then today we said we can now write C++ functions that build upon that take those basic cell definitions, query signals in the environment like contact with neighbors or extracellular variables or the amount of damage, and then modulate the cell behavioral parameters, things like how quickly you die or how quickly you're born, or even your motility or other properties. And so we have modulated that. Today, the next session after the hackathon part will be an optional session on 3D visualization using a beautiful platform called Simularium written by the Allen Institute. And then we'll have an asynchronous overnight session on visualization in Fury as an alternative. The one that you may want to make sure you really do is watch the video that's going to be online very soon on PhysiBoss, the Boolean network stuff, because tomorrow morning our good friends at Institute Curie will be giving a demonstration of how to write Boolean signaling models as intracellular models and couple those into PhysiCell agents. And then for Con, we'll continue that theme in the afternoon to say how we would tie systems of ordinary differential equations into cell agents and model that. And then by tomorrow evening, I will have one more set of slides available for asynchronous that will show you some of the more advanced contact-based interactions for some of those who need it. I'm going to go ahead and stop my share and see if there are any extra questions here. So I'm seeing mostly internal conversation, which is really, really good. So Julio, you have asked a really great question. Where do you get the behavior names? And so I'm going to make like a glossary on that and release that sometime overnight tonight. But again, I have a cheat, and I think you'll like this. Actually, you may not like it. But what I do is I take my project name and I run it just a little bit, because actually the code will auto-generate these dictionaries and list out the dictionaries at the beginning of that standard output. So what I do is I run the model for, let's say, just a couple seconds and just pipe it into a text file. So like project arrow dictionary.txt, that's enough. And so now I'm going to open up that dictionary and I'm going to scroll through, and I have my dictionary of signals: food, quorum, zombie, intracellular food, quorum, zombie gradients, mechanical pressure, volume, contact with any of the cell types with a farmer, prey, or a zombie, contact with a live cell in general, contact with a dead cell in general, how damaged am I alive or dead, how long have I been attacked, what's the current simulation time, or any of my custom variables. Those are my signals I can very easily query. And then here are the behaviors I can modulate: secretion rates of food, quorum, zombie, secretion targets, uptake rates, net export rates, cycle entry rate. Now, cycle entry is the same thing as exit from cycle phase 1, so that's synonymous. Apoptotic and necrotic death rates, migration speed, bias, and persistence time, chemotactic sensitivities this is for the advanced chemotaxis, cell cell adhesion and repulsion, adhesive affinities, which are usually just 1, maximum adhesion distance, so a lot of the mechanics can be modulated, phagocytosis rate of either a dead cell or any of the live types, attack rates, fusion rates, transform to some cell type, and then the custom variables. So if you want a quick reminder, auto-generated, you can basically pipe that beginning text output to a text file and see what was spat out as a dictionary. And what I'm going to do is I'm going to probably revise the code in the next release, but probably not this week, to actually auto-generate that dictionary at the beginning of the run. It was a really good question, something that I have to do very manually right now. Down the road, what I want to do is to actually have a GUI. I can say, pull down, make a rule, say, drop down, say, input is this signal, and there's a dictionary of signals. Behavior I want to modulate, and then is it increase or decrease? And then do I use like a linear response? Do I use a quadratic? Do I use a Hill response? How do I modulate the behaviors of that response to actually generate a rule? And that's something we want to start building over time. So cool. Let's see here. Serhi asked if the megazombies also have a target volume. They do. So actually, when two cells fuse, the new target volume is the sum of the two old target volumes. So unlike phagocytosis, where they'll shrink back down, bigger fusion will make things bigger and they'll be persistently bigger. You could make a rule that adjusts that size, but right now, mega just gets mega, mega, mega. Any other questions? Well, thanks very much for following along. It looks like we have a very short break, like 10, 15 minutes. I think first of all, let's stop the recording.